स्मार्ट माइंड्स ट्यूटोरियल सफलता का आपका प्रवेश द्वार।
Let us cover some more questions on uniformly continuous functions. So take the first question. Show that f of x is equal to 1 by x square is uniformly continuous on a comma infinity, where a is closed and infinity is open, and where a is greater than 0. That means a is positive. So first let us write the given function. So given function is f of x is equal to 1 by x square. Let epsilon greater than 0, then there exists delta greater than 0 such that x is greater than or equal to a, y is greater than or equal to a, and mod x minus y is less than delta. That implies mod f of x minus f of y is less than epsilon. Now let delta is equal to epsilon a cube by 2. Now we will consider mod f of x minus f of y is equal to mod 1 by x square minus 1 by y square. That is equal to, if you take the LCM, y square minus x square by x square y square. Now numerator is in the form a square minus b square. We can write it as a plus b into a minus b. So y minus x into y plus x by x square y square. Now to separate them, we can write less than or equal to mod y minus x mod y plus x by x square y square. This is less than or equal to, now mod y minus x is delta. So this is less than or equal to delta mod y plus x by x square y square. Now this is less than or equal to delta into, now we need to separate it. So how to separate y by x square y square plus x by x square y square? Y cancel, x cancel. So less than or equal to delta into 1 by x square y plus 1 by xy square. So that is less than or equal to delta into 1 by a cube plus 1 by a cube. If you add them, what do you get? 2 by a cube. 1 by a cube plus 1 by a cube is 2 by a cube. This is less than or equal to delta, we can write epsilon a cube by 2 into 2 by a cube. A cube, 2 cancel. That is equal to epsilon. Therefore, the function f of x is uniformly continuous on a comma infinity, where a is greater than 0 and a belongs to R. Take the next question. This is also important. Prove that a real valued function f on open interval a comma b is uniformly continuous on open interval a comma b if and only if it can be extended to a continuous function f on closed interval a comma b. So let's see how do we prove this. So first we will write what is given to us. Given that f is a real valued function on open interval a comma b. Open interval means it lies between a and b, excluding a and b. Okay. So now here we have two cases. Case 1 is let f be extended to a continuous function f on closed interval a comma b. Since f bar is let's take f bar here. So since f bar is uniformly continuous on closed interval a comma b, which implies f is uniformly continuous on closed interval a comma b. Now let us take case 2. What is case 2? Let f be uniformly continuous on open interval a comma b. So let us define f bar of a and f bar of b such that the extended function will be continuous. Now let us consider the function f bar of a. Here we have assertion number 1. What is assertion number 1? Let Sn be a sequence in open interval a comma b that converges to a. Since the sequence Sn converges, if it converges, we can say that it is a Cauchy sequence, because every convergent sequence is a Cauchy sequence. Now since if f is uniformly continuous on a set S and Sn is Cauchy sequence in S, then f of Sn is a Cauchy sequence. That implies f of Sn is also a Cauchy sequence. Now since a sequence is convergent sequence, if and only if it is Cauchy sequence. Hence, f of Sn converges. Now let us take assertion number 2. What is assertion 2? Let Sn and Fn, or let Sn and Tn, let us take Tn be any two sequence in open interval a comma b, both converging to a. Now let un be any sequence such that Sn and Tn are both subsequences of un is defined as un from n is equal to 1 to infinity is equal to S1T1, S2T2, STT3, so on. Now which implies limit n tends to infinity, un is equal to a, which implies limit n tends to infinity, f of un exists. Now, since f of Sn and f of Tn are subsequences of f of un, then both must converge to the same limit. That is limit f of un. Therefore, limit n tends to infinity, f of Sn is equal to limit n tends to infinity, f of Tn. Now let us suppose that assertion number 1 and 2 both are valid. Assertion 1 and 2 are valid. Thus, define f bar of a is equal to limit n tends to infinity, f of Sn for any sequence Sn in a comma b that converges to a. So here you can see assertion number 1 guarantees limit exists and assertion number 2 guarantees limit is well defined and unique. Thus, f bar is continuous at a. Hence, from cases 1 and 2, what can you say? A real valued function f on open interval a comma b is uniformly continuous on open interval a comma b if and only if it can be extended to a continuous function f bar on closed interval a comma b. Hence the theorem.